Good afternoon, everyone. My name is Chuan, a PhD student of MOWT, advised by the professor. Today, my report topic is about the performance calculation between the monopile of the wind turbine and the jacket of the wind turbine. I will briefly introduce it from the following three parts. As we all know, for the floating of the offshore wind turbine, we can divide into the fixed mode and the floating mode. According to the global wind report, by the end of the 2023, the installed capacity of the floating offshore wind turbine is only around 236 megawatt. For the most of the offshore wind turbine is a fixed type. It accounts for over 99%. So today, our research mainly focuses on the fixed type. And we know for the fixed of the wind turbine, according to the different work tips, we can use the different substructures. For the monopile offshore wind turbine, it is suitable for the work tips below to the 30 meters and account for the 80% globally. And for the jacket of the wind turbine, it is used for the work tips between the 30 to 60 meters and account for around 80%. However, we know with the trend of the offshore wind energy development toward to the deep waters and large size, so some scholars and companies they propose the XXU monopile concept with the diameters between the 8 to the 12 meters and length from the 40 to 120 meters to replace the jacket substructures. But it is possible for the XXU monopile of the wind turbine to compete with the jacket of the wind turbine in the transitional workers. So in our research, we will make this course. And the first is the numeric model. And if we want to compare different substructures for their dynamic performance, for the monopile and the jacket, there are differences in the mass and stiffness and the natural frequency and some other properties. So if we want to make a fair comparison between these two substructures, first we have to make a principle to keep these two structures to be same. And maybe we can keep the mass of this both of the structure are the same, or we can keep the stiffness to be same. But in our research, we keep the natural frequency of these two offshore wind turbine to be same. And also we proposed 5 design constraints and 3 key variables to make an optimized design for the offshore monopile offshore wind turbine in the transition waters. And for the 5 design constraints, first we need to keep the same turbine and tower configuration. And also, in our simulation, we need to ignore the mass and stiffness effects caused by factors like the grouting or the wave welding. And also, for these two structures, we keep the same design water tips and environmental conditions, and also material and design load cases. And also for these two structures, we also need to meet the SLS and ULS and FLS requirements, and also some other design criteria. For example, for the monopile of the cylinders, we need to less than 10 to 20, and for the diameter to the thickness, we should less than 100 to the 120. And for the 3 key variables in here, we choose the pale diameters, pale thickness, and pale embedded lengths. Those are related equations. And for to optimize the progress, I will not introduce it more. And this is our final geometric dimension of the proposed observing turbine for the monopile and jacket. And finally, we have the natural frequency. For the first natural frequency to be 0.28 Hertz, and for the depth is 50 meters. And there are some basic parameters in our simulation. This is the environmental condition and material property and soil profiles. For the environmental conditions in here, it shows two different environmental conditions. One is for the normal condition, the observing turbine rings, and one is in the abnormal condition under the extreme environment. And for the materials, mainly include the steel and the concrete. And for the soil profile, we just choose three different: soft, medium, and hard. And this is the external loads and design load cases. For the external loads, here we mainly include three types. One is the initial static loads, mainly include the gravity and hydrostatic pressure. And for the aerodynamic loads, there are mainly two loads. There are aerodynamic loads acting on the turbine, and another being the load is acting on the tower. And for the hydrodynamic loads, mainly from the wave and current, those are some equations. And this is the design load cases. In here, this slide is the design load cases 1.1. This is for the power production conditions. And for the design load cases 6.1 is for the packed conditions under the extreme environment condition. We can check it from the DME core or the IEC core. And this is our final numerical models. This is for the monopile, and this is for the jacket. And for the monopile, we have the fixed foundation, and also in here we also build the flexible foundation. And for the jacket of the turbine, it's the same. Then is the last one is the results and discourse. And first, we check the dynamic response. First, we check the first natural frequency of the monopile and the jacket. We can see in here, this is for the fixed foundation. You can see for the monopile and the jacket of the turbine. This in here, it's around 0.3. And this is for the flexible foundation for the monopile of the turbine and jacket of the turbine. You can see this is the state. And also in here, for the first natural frequency, we have to avoid the external exciting peak frequency for the Y in here and for the wind. And also we need to avoid the 1P and 3P. 1P means the total frequency in this range. This is the 3P. This is the blade passing frequency. You can see it's in the outside of this range. So to avoid the rings. And then we check the top displacement and the stress. For the top displacement of the orbital turbine, we have to less than 1/200th of the effective length of the structure in here. And for the stress unity ratios, we should less than 1. It is compared with the allowable stress. In here, we can see in the for the displacement of the monopile and jacket, we can see it has a big difference. The monopile of the turbine under the same load condition, we can see it's larger than the jacket of the turbine. The difference is around 49%. And this is for the fixed foundation. If we consider the foundation use the very flexible, we can see the difference is around 40%. And for the stress, we can see for the fixed foundation, the monopile and the jacket of the wind turbine, the difference is around 26%. and the monopile is larger. And for the flexible, this too is similar. And then we make a sensitivity analysis to the environment conditions and also soil properties and embeddedness. First, we can see the effect of the environment conditions. Under the different wave directions, this is the difference of the tower top displacement, and this is the stress difference. We can see for the monopile and jacket of the wind turbine for the fixed foundation, you can see in the displacement, the monopile of the wind turbine, it will vary. The variation is around 22%, but for the jacket of the wind turbine, it's only 2%. For the stress, we can see the monopile of the wind turbine, it will raise to the 62% around. But for the jacket, it's only 2%, 2.5%. And for the flexible foundation, we can see also for the monopile, it will have a big sensitivity for the environment condition. It will vary, the variation is very large. For the jacket of the wind turbine, it's small. And in here is the soil properties. But for the effect of the soil properties, there it has a different effect. We can see for the monopile of the wind turbine, the variation in the frequency and displacement and the stress, we can see the variation is relatively small. But in here, we can see for the jacket of the wind turbine, the variation is larger, especially for the displacement, the total displacement. So the jacket of the wind turbine is more sensitivity to the soil property. But there we need to note, also the jacket of the wind turbine is sensitivity to the variation for the soil property. But we can see the total displacement and also the stress is impacted the maximum amplitude is still lower than the monopile of the wind turbine. And this is for the effect of the highly embedded lengths. Also, the jacket of the wind turbine have a big sensitivity. You can see for the total displacement, the maximum variation for the jacket of the wind turbine is around 32%. But you can see for the monopile of the wind turbine, the variation is only 9%. So the jacket of the wind turbine is sensitivity to the variation for the pale embedded length. But also we can note the maximum magnitude for the displacement stress, the monopile of the wind turbine is still larger. And also we make a mass assessment between the monopile of the wind turbine and the jacket of the wind turbine. We can see that for the total mass, it has a 16% difference. For the jacket of the wind turbine, it's lower, around 60%. So in summary, in here we make all of the performance compression. In here, this is the conclusion because the jacket of the wind turbine has the obvious advantage over the monopile of the wind turbine in the total displacement, deflection, and the stress yield and environment condition change, and also the mass. And monopile of the wind turbine performs better in withstanding changes in the soil property and also the pale embedded length. But we should notice that also the dynamic response of the jacket of the wind turbine is sensitivity to the soil properties and pale embedded length, but it always have a smaller while compared to the monopile of the wind turbine. And this is our public paper for reference if needed.